Well, hello. Maybe you saw me yesterday already. So I'm Juan Pablo Vigneaux. I'm currently unaffiliated. So this is my personal email in case you want to get in contact, get in touch. But I will also start at Caltech this September. So maybe then you will be able to find me there too. Well, and I have a website also, so whatever. So I want to talk about information cohomology. So it was this idea introduced by Baudot, that's here, and Baudot and Bennequin, that was yesterday around. And the idea of this theory is to associate certain algebraic invariants to sheaves or functors over categories of the statistical observables. So it's some sort of generalized geometry, if you want. So you start with a category of observables, and that would be something like your category of open sets. And then you consider these secondary objects that you can define on this. That would be these functors. And then you want to compute the invariance of this. And it turns out that the entropy appears in this context as an invariant of a functor of probabilistic functionals defined on this category of observables. And then so the entropy defines a cohomology class in degree 1, and the fact that it's a cocycle in this theory encodes the chain rule of the entropy. But it's not only that the entropy satisfies the chain rule, so it's a one cocycle, it's the only cocycle. So it's like there is also this unicity side of it. So in this sense, the entropy, the chain rule, is a defining property of the entropy. It characterizes it as the unique one cocycle in this algebraic framework. And one could ask, well, does something similar hold for the differential entropy? And what I'm going to show is like the answer is yes, but to exploit what we know already, so we need a category that mixes discrete variables and continuous variables. And again, we are going to take the coefficients of the cohomology in this sheaf of probabilistic functionals. But this time, we are going to ask for these functionals to be continuous in the total variation norm. And so again, we get these cocycles equations that are functional equations, and then the idea is to solve these functional equations. And turns out that the only solutions are, well, of course, there is a discrete side and a continuous side. So on the continuous side, the only solution, the only one cocycles are convex combinations of the differential entropy and the dimension of the underlying space. So the dimension appears somehow as a second information function in this sense. So I'm going to explain the details of this. So more formally, well, yeah, I want to introduce this more formally. At the same time, I don't have much time, so I think I won't enter into all the details, but of course they are in the paper. So more formally, when we introduce a category, a poset of variables. So the arrow in the category encodes purely algebraically the fact that X is coarser than Y. And to each object of the category, we also associate a measurable space that is like the space of possible outcomes of this variable. And this functor is such that, like, if you have an arrow like that, then you obtain a surjection between EX and EY. And the product in the category S is supposed to represent the joint measurement of the variable Y and Z. So the values that you associate to this joint measurement are injected into the product of EY and EZ. So this means that if you give me separately the value of Y, the value of Z, then we can determine the value of the joint, but this doesn't mean, of course, that this set is equal to the product, okay? So there could be additional constraints. Well, and also the category has a terminal object that we denote like that. That is like a certainty. And the probabilities and many other things appear then as secondary objects, so as a functor on this category S. So for example, you can associate to each object X the set of probability measures on X, and this will define a functor because for each arrow in the category S, you will have a map that is just taking the image measure under the projection EP. So you have these functorialities. So this is the full functor of probabilities, but in this continuous setting, sometimes you have to restrict because there are just too many probabilities. So more generally, we work with subfunctors of this functor, but we ask that they are stable by conditioning. So conditioning is understood in this context also as disintegrations, as in my talk yesterday. So the conditional measures are actual measures. They are not functions. And you ask for all these conditional measures to also belong to the functor of probabilities. So you have, of course, this closure property. And then, so that is like the fact, so that you can introduce these categories and that many things like probabilities come as functors in this category. And then the algebraic side that is related to this chain rule that I show is the fact that when you fix a variable and you see like all the variables that are coarser than that one, there is a natural notion of product that is given by the product in the category. So you have like this monoid. For each variable x, you have the monoid of the variables that are coarser than it. And of course, this comes as a shift because for each x, there is one of those and it's contravariant with respect to the arrows of S. And well, this A is just turning this into an algebra. So it's the algebra induced by the monoid. And once you have this sheaf of algebras, then you can look at modules. So the modules are like usual modules, but now also there is one for every x and everything is naturally next. No? So we are all working all the time with functions, but maybe you have with functors, but maybe you can forget that in some statements. And this module comes, of course, then with an action of the monoid. So normally we introduce the action of the monoid and just extend it linearly. So the main example is this one, so we call F. So it's the measurable functions on Q. So for each x, you take the measurable functions on Qx. It's contravariant because the morphism is precomposition with marginalization. So the morphism FP is precomposition with QP. And the action of the variables on these measurable functions of probabilities is defined in this way. So you, for each variable that is coarser than x, you can get a new functional that is computed as the average, if you want, with respect to the image law on y of this functional evaluated on conditional loss. So this is like the Shannon action, if you want. So this is the way the conditional term, for example, that would appear in the chain rules for the differential entropy, things like that. So are there questions up to this point, or because maybe the notations are a bit messy, but that's okay. So this is the. And of course, well, this is an action of Sx on this Fx. So this is non-trivial. It's the fact that if you act with y and then with z, it's the same thing as acting by just once with the joint. So this is the thing that one has to verify. And it's not as trivial as it sounds. Then information cohomology, then can be introduced in two different ways. So there is an abstract way of doing it through derived functors. And then it's very analogous to group cohomology. So you can introduce it as a derived functor, but then you can also introduce this bar resolution and turn it into get like an explicit description of it. So in fact, here we also use a bar resolution. And we get an explicit computational description of the cohomology that I'm not going to explain in general. I'm just going to explain what is H1, because this is the entropy appears in degree 1. So in degree 1, where it's easy because there are no coboundaries. And so you only have to explain you what's a cocycle. So a cocycle is a certain kind of cochain. So first, what's a cochain? Well, a cochain appears as a natural transformation between the coefficients we are going to take probabilistic functionals here, and this shift B1. And this V1 is a module freely generated by these symbols. So you take one bracketed symbol for each variable that is coarser than X. So this will be a one cochain. And since this is a freely generated model, of course, you only have to determine these quantities, so the images of the generators. So these are the unknowns of the theory, if you want. So in order to determine a one cochain, you have to give me all these functions. But I'm going to simply denote in this way to simplify a bit the notation. But then there is a first thing that appears that there is a naturality. So in fact, this function on X only depends on its marginalization on Z. So well, Z is the bracketed thing. So there is a notion of locality. So this is the notion of locality. So the function bracket Z only depends on the marginalization of the law on the variable Z. And now the condition of being a one cocycle, well, it's like a boundary condition, and it's this thing being equal to 0. So this is a functional equation because these, they are all elements of Qx. These are measurable functions of probabilities on X. So this cocycle equation relates three different unknown functions on Qx. So this is how you get systems of functional equations. So for each pair of variables like this, you will have one functional equation, such as this one. And the collection of all these functional equations is the condition of being co-boundary. It's a cocycle. And now, so can we solve this? Well, the answer is yes. So in the discrete case, this was done in...
There's no x2 is like the previous one.
Yeah?
It's not x2, x1.
Sorry, no, there is a mistake. No, wait. No, it's x1 acting of px2, then minus phi of joint, and then plus phi of x1. No, it's okay. Yeah. So of course, if you put this on the other side, then it looks a bit like the chain rule. So this is where the connection appears. So this is why the entropy is a cocycle, but then the thing is showing that it's the only cocycle. So the entropy is clearly a cocycle because it satisfies the chain rule, but then one can show with functional equations, etc., the results already existing, that is the only. So this is the first result that was shown by Daniel and by Pierre, and then refined a bit by me. And in the continuous case, it's a bit more complicated. Just like the set is how to define the good setting, but then the category S is taking, well, I almost have no time, so I think I won't talk about what I wanted to talk about, it doesn't matter. So you fix a category for spaces with space E. This will be your category S, then the values will be the quotients by these spaces, or explicitly you can, we will identify these quotients with the orthogonal of the spaces here. Well, etc. I think this is not so important, maybe. But well, you have to introduce a notion of support. Maybe I will only show you this drawing. So the thing is, okay, now you will have these spaces. You want to consider laws that are support on affine spaces and that have a Gaussian law with respect to a Lebesgue measure on these affine spaces. And but you cannot stay with a fixed dimension of these affine spaces. For example, you could consider only non-degenerate laws. Maybe you want to consider only non-degenerate laws that are supported on the whole space. But you cannot, because you will project these laws, so still you will have non-degenerate laws, maybe, but then you will take conditional probabilities, and the conditional probabilities will be supported on the fibers of the projection. So then you will decrease the dimension. So here, for example, if you project this, well, you get this other one that is supported on a line, but then if you condition, then you have these other Gaussian measures, also Gaussian, but supported on these spaces of smaller dimension. And the remark is like the dimension of the support is already a cocycle, and this is the nullity-rank theorem. So the dimension of this whole space can be computed as the dimension of the projection, so the dimension of the marginal law, plus the dimension of the conditional, the support of the conditional probabilities. So the dimension itself is a cocycle, and the differential entropy gives another cocycle, and then the difficult theorems to prove these are the only ones. And this is the theorem that appears in my thesis. So this is for Gaussian laws. Okay, so already 15 minutes, so this should already be over, but well, what are we going to do? No, so there's still 5 minutes, no questions. So this is the characterization of one cocycle for Gaussian laws. So you have the dimension of the support and you have the differential entropy, and this in this case is just essentially the determinant of the covariance matrix. But it's important here that you cannot fix a basis anyway. You have to work in a base-free manner. Otherwise, you have like spurious cocycles. And now the purpose of this talk was to mix both. So to mix these continuous and discrete results. So for that, you have to consider a product of two information structures. So one that has continuous variables, the other has discrete variables. And of course, at the level of values, of possible values, you get these products also of a continuous set with a discrete set. Of course, you can see the original ones as some sort of subcategory of the product. So in this sense, you can embed the continuous structure and the discrete structure into this product structure. And locally, if you only work with the continuous part or the discrete part, you can recover the results that I just showed. And now the idea, so you have a characterization of the one cocycles on this continuous part, discrete part, and now the idea is to see what happens with the other objects. So those that are actual products, non-trivial products of discrete and continuous things. And this is what I wanted to show. So I think I'm also going to show just the drawing. So it's this. So on one side, so in blue, so this would be a discrete variable. In this case, it takes 3 possible values. Here you have a continuous variable. In this case, it's just the real line. So then this variable set is a non-trivial product in this mixed category. So it's the product of this space, this real line with these 3 points. So it looks like 3 lines. So if you have a reference measure here, that is some choice of Lebesgue measure, this will induce a reference measure on this more complicated space because you will just inject this Lebesgue measure on each fiber. So you have a reference measure on this space, and now you can consider a general probability law will be a law that is absolutely continuous with respect to this reference measure, and can be written in this way. So it will be a sum on the fibers of certain probabilities times certain densities. So in this case, I just took Gaussian densities. Times the Lebesgue measure that is supported just on this line. So the line associated to certain value of y. So it will look like this. So it will be this. There will be one density for each line. Now, if you project this to y, you will just get a discrete law with these weights that are the areas of the curves here. If you project it to the other, so to the space X, what you get is a mixture of Gaussians. So we exploit this property. So if you want to compute the cocycle on this law, that is this complicated law that I just showed, you can do it in both ways. So you can first project to the continuous part, so you will get not the entropy, the cocycle evaluated on a Gaussian mixture. And then you will get this conditional term where all these laws are discrete laws, because the fiber over each point of the real line look, in fact, like a discrete set. Or you can start projecting to the discrete variable, so you will have the cocycle evaluated on a discrete law, plus this conditional term, and now it's just a sum because it's discrete, of this cocycle evaluated on Gaussians. And the point is, we know how all the cocycles evaluated on Gaussians are. This is just the characterization theorem that I show. It's just the determinant plus the dimension with some constants. And we also know how the cocycle looks on discrete laws. So every cocycle in a discrete law is Shannon entropy. So similar here, this is Shannon entropy. And this, well, this we don't know, because we don't know the cocycle phi. But we know this term, we know this term, we know this term, because we have this characterization. So I'm already over. 1 minute. 1 minute. So the thing is, yes, so this is the unknown that we can write like this, but all these terms we know. And now the only final idea is that one can approximate every density with a Gaussian mixture. So this projection was a Gaussian mixture, but now if I assume some continuity, with not having this explicit formula for the cocycle on a Gaussian mixture allows me to approach the value of the cocycle on any law. And this is like the final theorem. So using this approximation, this is called the kernel estimate, I can prove that, well, a lot of hypotheses on convergence, that every cocycle looks like a combination of the differential entropy and the dimension. Well, that's it because the time is over.